Welcome back. So today we're going to start talking about space and momentum, right? And these are topics that you have covered already once in some other physics classes, but we're going to do it today from really the perspective of quantum mechanics, in the sense that we're going to use all of the tools that we have available to us, all of the linear algebra, all of the intuition that we have for what it means to be a state, and all of the spookiness that comes along with quantum mechanics, to really understand what it means to talk about space and momentum when I'm talking about it as a quantum mechanical property. And I'm going to ask you to do something very carefully, because I'm going to talk about these concepts at a level that is a little bit different than the level in your book. So I'm going to ask you to watch this video, then I'm going to ask you to read your textbook afterwards, and then probably watch this video again, because I want you to think about this idea of space in the language that we've been using to talk about spin, rather than thinking about the quickest way to get to the answer to the problem. Okay? And so for that, I really want to go back to our basic roots and think about what it means to ask a question quantum mechanically. Right? And so when we developed the idea of a quantum state, right, I think the first time we did it was really in our first video, right, where we thought about a Stern-Gerlach experiment, and that experiment then had outcomes, it had measurements, and I built my state as a sum, right, or as a superposition, or as a combination of those possible measurements. It was the measurements that told me something about my Hilbert space. And then I was able to talk about really the thing, right, the state, as being defined by those measurements. And so, as I said, the example that we go back to is, right, this two-dimensional thing, right, where I had two outcomes of the Stern-Gerlach experiment, and I said that my general state, psi, is going to be a superposition. It's going to be alpha plus beta minus, right, where alpha and beta are our probability amplitudes, right? And that then began this entire idea of deconstructing my object onto the possible measurements of some operator, onto the possible measurements of some piece of apparatus. And we've also talked about much bigger Hilbert spaces, right? So higher spin systems or Hamiltonians, where I can now take my state and I can decompose it onto this larger Hilbert space, where I have many different expansion coefficients. In other words, I have lots of probability amplitudes. Each amplitude corresponds to the probability amplitude of being in a particular state, or in being in a particular pure state, being in an eigenstate, having some measurement, right? These are the words that we use, that the state is decomposed onto possible measurements of some operator. And these measurements were all answers to some question, right? The Stern-Gerlach experiment in the z direction was asking, what's the magnitude of the z component of the spin, right? Or actually, we started with the z component of the magnetic dipole moment, but what was the z component of the spin? What's the energy, right? These were questions that I built a device to answer, and the outcomes, right, were each independent eigenstates. They were each independent eigenvectors, and the eigenvalues associated with those eigenvectors were the answers to the possible outcomes of that measurement, okay? So far, though, everything we've talked about has been discrete. That is, there have only been a set number of possible measurements, and those measurements all had integer, I could line them up, right? So now I'm going to ask perhaps the most sophisticated question that you can ask in quantum mechanics, at least up until this far, and that question is, where are you? Okay. And this is a question that we've been skirting around, right? Because we've even talked about, measuring the spin in some apparatus, some Stern-Gerlach apparatus, but we've skirted around the idea of, well, where is that apparatus, right? If I detect a particle in a scintillator, right, I'm asking the question of, where is that particle, right? The question is, where are you? And therefore, because we know, right? I mean, I can put the Stern-Gerlach experiment here. I can put it on the moon, right? I can tell it the difference between measuring that silver atom, no matter where it is, right? Like I can tell the difference between being here and on the moon. Even me, right, can do that experiment. And so I have an operator then that can ask the question of where are you? That operator has some answers, right? X equals 2, X equals 4. X equals 7. We're going to restrict ourselves to one dimension here, okay, right? But you can be anywhere on the X line, right? So those positions on the X line now tell me I am here, right? In the same way that the up beam out of the Stern-Gerlach experiment told me that I was in the spin up state. And so every position along the X-axis, right? Every position along the number line is an eigenstate of the position operator, right? It's an answer, right? It tells me I am here versus I am over here. And I should be a little bit careful about the answer because the measurement associated with that, right? If I take my X operator and I say this location is an eigenstate, it's a possible, state for X to be, right? I measure the thing here. Then the eigenvalue associated with that is going to be, well, what's the value of X right here? Okay? And so if I take so now I'm going to just write out a number line and I'm going to have some special point, I'm going to call it X star. And I know that point is going to be an eigenstate of the X operator, which means that I can act the X operator on X star, and I'm going to get out something proportional to X star. And that constant of proportionality, the measurement, the eigenvalue, the whatever word you want to call it, is going to be that location, right? Now, there are a lot of x's in this equation, and part of me feels like, man, is this the silliest thing you can possibly write down? But it really contains 3 different x's that all mean very important things, right? There's the x with the hat on it, and I'm going to now kind of go back to my desire to put hats on top of operators, just because when you have so many x's, it kind of matters which one's the operator. But I have this x operator. I have X star, the ket, which is a location, right? It's a state of being. It's saying the particle is at X star. And then I have the eigenvalue X star, which literally gives me the eigenvalue, right? It literally answers the question, where are you? I'm at X equals 4, right? I'm at X star. That's the eigenvalue associated with the eigenvector, which is the place. Right? And that's a really subtle thing. So I'm going to say it probably 2 or 3 more times, right? The eigenvector is where are you? Whereas the eigenvalue is the answer. I'm here, right? In the same way that top beam coming out of the Stern-Gerlach experiment that said, I have spin h bar over 2. H bar over 2 was the answer, right? That's the measurement. But the beam coming out, those were the particles that, had that value, right? And so this location on the x-axis is the eigenvector, and the value of that location is the eigenvalue. And of course, there are lots of eigenstates here. There are an uncountably infinite number of eigenstates here, which is why it's really hard to come up with a different symbol for the eigenstate and the eigenvalue, because there's so many of them, right? I can't index them by sub I, right? There are certain things that I could do with a discrete set that I literally cannot do here because there are just so gosh darn many of these eigenvectors, right? There's literally one at every point on the number line, which we all know is an awfully big space, right? That's an awfully, awfully big infinity. And yet, I still have to impose this, knowledge that every state on that line is independent, right? If I see this particle at x equals 2, it's not at x equals 4, right? The scintillator picked it up here at x equals 2. It's not at x equals 4. It's not on the moon. It's not at Alpha Centauri. Each of these points is independent, which means that I need to make sure I understand that the dot product between those points is almost always 0, right? That's what independent means. In fact, the only time when it's not 0 is when x1 is equal to x2, right? If I have 2 different points, x1 and x2, the only time that they're not the same is when they're the same, right? And of course, we'd love to use that Kronecker delta, but that's awfully discrete, right? And so we have to rely on our other favorite delta, the Dirac delta, to represent what happens when I have the product of x1 with x2. And so we know that this must be x1 minus x2. Okay, the Dirac delta tells me if x1 is not equal to x2, the inner product of these two eigenstates is 0. That in English, that just means x1 and x2 are in different places, right? But if they're the same, then this delta function is not going to evaluate to 0. You might worry it's infinity, but anytime we use it, there's going to be an integral sign, so don't worry about it now. Okay? Actually, don't worry about it ever. You're never going to have the delta that's not underneath an integral sign, and you'll see why in a moment, okay? But despite the fact that this space is infinite and uncountable, it's still independent, right? I still have a bunch of independent states. I have a heck of a lot of independent states. So now I have all of the building blocks for doing something really cool and sophisticated, right? In the before time, right, what I did was I took my state and I decomposed it onto the eigenstates of my operator. I want to do exactly the same thing here. I want to take some generic state and I want to say that it's built out of all of the eigenstates of the position operator. That's no problem. The problem is that before I was able to line up all of these states from 1 to n, and I could sum over them, but here I can't do that, right? Because my states aren't countable, right? I can't say a sum of I equals 1 to infinity even, or minus infinity. I can't do that sum anymore. And so when my states are so close together that they're continuous, I take my sum and I replace it with an integral. And so I have now the integral over all possible states times something that I'm going to call psi of x for a moment, but I need a set of probability amplitudes, right, that tell me how much of my state is in each one of the eigenstates. But the discrete to continuous transition here is something that we really need to spend a minute on, because the idea of having a probability amplitude associated with a discrete state is something that's somehow easy for us to picture because I can write it down in a vector. But the probability amplitude associated with a continuous set of eigenstates is much harder to think about, right? Because now I'm saying for every single state x, there's some probability amplitude of being in that state. But of course, since x is continuous, the function that describes those probability amplitudes, which I'm calling psi, must also be continuous, right? That it is now not a set of discrete pieces of information. It's a continuous function that helps me to map out what are the probability amplitudes of being at any of these eigenvectors. And so what I end up with is this very fun decomposition of my state onto the structure here, which is a description of the probability amplitudes for every point on the x line. Okay? It's a collection of probability amplitudes. It tells me what's the probability amplitude for being at any place x. And that's the thing that we call the wave function. And it's important not to use that word until now, because the wave function is a set of probability amplitudes. It's just a continuous set of probability amplitudes. And it's something that we should neither be afraid of, because we understand how to decompose a state onto a continuous set of eigenstates. We did it in 245. But we also shouldn't be too quick to jump to this wave function, because its meaning is held up in the fact that there's an x operator, and that x operator defines the set of states x. And this is a way of writing the wave function that's totally correct, no matter who you are or where you're from, right? This way of writing down the definition of the wave function is true and right and just and excellent, okay? And it comes from exactly the place where we know probability amplitudes should come from, right? It came from having an operator that had a set of states and a set of expansion coefficients that go along with those states. I guess I already wrote this. So how do I visualize the wave function? Well, some people, and we will also plot maybe the real part of the wave function and the imaginary part of the wave function. These are important things to be able to do. We're going to be solving for wave functions. We're going to be talking about wave functions, wave function, wave function, wave function. But it's really best, I think, to start to not think about plotting the wave function first, but to plot the square of the wave function, which is, of course, the probability distribution, right? The wave function is the set of probability amplitudes. If I take the modulus of that squared, psi star psi, then I'm going to get a number that's real and greater than 0, right? It's a magnitude. And that then tells me, well, what's the probability of being at any point? And now, okay, right, now this makes sense, right? This piece of information, the modulus of the wave function, is really giving me a plot, a chart, of where am I most likely to take a measurement of that particle? Where is the probability of the particle being at some point is larger than the probability of the particle being at some other point. And that's something we even talk about in statistics class, right? This is a beautiful thing that helps to tie in our intuition for what it means to be more likely somewhere than somewhere else. And so now, using this probability density, I can actually start to answer some questions, right? So for example, what's the probability at being at this point x1? Well, that corresponds, of course, to, well, what's the probability amplitude of being there? Well, that psi of x1. The probability of that is just going to be that squared, which is psi of x1 star psi of x1. Right? That tells me the probability, right, of being in some place. Now, of course, it's really measuring at x1, that doesn't feel so great, right? Because even though that might have a non-zero value, x1 is a pretty skinny place to live, right? I mean, there's just not a lot of width there, and so when I build my scintillator, I probably am more interested in, it's between x equals 1 and x equals 2, right? It's sort of better to think about what's the probability of being in some region. This is a measurement that I can probably do, which of course is the combined probability densities of having all of those points between x1 and x2. Right, and so what question am I going to answer there? Well, I'm going to answer, well, what's the probability of being from x1 to x2 of psi star psi dx, right? And that thing then is really the probability of being between two different points, because I can integrate the probability density. And I should probably say, what's the probability density here, right? Just so that I get my units right that I'm talking about probability density. Of course, what's the probability of being somewhere? That is, what's the probability of being, I don't know, between minus infinity and infinity of psi star psi dx? Probably 1, right? That is, you got to be somewhere if you're anywhere. And so now we've stumbled upon, by thinking about this probability density, of really what it means to be normalized as a wave function, right? That you have to be somewhere, and if you're somewhere, then you got to be somewhere, and so the probability of being from minus infinity to infinity must be 1. Okay, so we can build a lot of intuition by thinking about this structure, which tells me, how likely I am to be in each one of these eigenstates of the position operator. Now, where does this get kind of cool or funky? All I've told you so far is that the eigenstates of the position operator are continuous. But that doesn't mean that eigenstates of other operators that contain the position operator have to be continuous as well. Okay? And that is, I might have some other measurement, right? Some other construction that means that only certain wave functions are actually allowed. And this should ring a bunch of bells from Physics 245 or perhaps Physics 145 or perhaps kindergarten when you were talking about the fact that boundary conditions can set rules that make it so that not every possible function is a solution to a differential equation. And so you can imagine that there exists some operator, hell, let's call it the Hamiltonian for no particular reason other than that's exactly what we're going to do for the next 4 weeks, right? And that Hamiltonian now has some information associated with it such that there are only certain allowed states of psi, right? There are only certain allowed eigenstates. Meaning that this Hamiltonian imposes some rules that tell me that there are only certain energies allowed in my particular system, right? We know that this exists, that there are electrons and atoms have only certain allowed energies, right? And so there must be places where the continuity of space is broken by the definition of energy somewhere. And so now I have a set of states, which I'm going to call psi sub I, where these psi sub i's are eigenstates of the Hamiltonian, not eigenstates of the position operator. But that is to say that these states exist somewhere, right? Just because certain wave functions are allowed and other wave functions are not allowed doesn't mean that they don't literally exist. And so I can take this state, right? Psi sub I is an energy state, right? It's a state that has definite energy from the Hamiltonian. And I can say, let me write that in terms of the wave function. And so I can decompose that state onto the eigenstates of the position operator, and I get this neat expression where psi sub I is related now to the specific wave function psi sub I of x, right? And this notation is going to be a little bit hard to get used to. If I have a psi of x, or if I have a wave function without a ket around it, that means really it's embedded inside this integral. But that's the thing that I can plot. Whereas the psi with the ket tells me that's the state, right? That's the thing that I can act on h with, right, to get my answer. But I know that because these states come out of a Hamiltonian, and they're all different states, well then there must be a Kronecker delta that defines the relationship between psi I and psi j. Well, I can use the formalism above, right? And I'm going to do some fun math here. I'm going to say that I need two different x's, right? Because I'm going to have two different integrals over x. And so I'm going to call one x, I'm going to call one x prime. So I have the integral from minus infinity to infinity of dx prime. I then have the integral from minus infinity to infinity of dx. I'm going to write both integral symbols here, although I tell you the truth, I don't tend to always do that. Now I have two of these copies, right? So I have my psi j, which is a decomposition onto the bra of x, psi j of x prime. And of course, it's the bra version, right? So I had to take the complex conjugate of it. I then have the ket version, which is psi I of x times x, and I forgot my x prime here, right? Because the bra is the one that's going to have the x prime. Well, my two wave functions are just numbers, right? They're not operators. And so what happens to this thing is that I end up with psi j star of x prime times psi I of x times x prime x. Ha ha! Those are independent, right? Not only are they independent, but I know that this thing has to be equal to delta x prime minus x. Which means that, I have my two integrals, dx prime dx of psi j star x prime, psi I of x, delta x prime minus x. A delta function allows me to do one of the integrals, right? And when I do one of the integrals, I end up with changing either the x primes to the x's or the x's to the x primes. I'm going to change the x primes to the x's. And so now I get the integral from minus infinity to infinity of dx, right? Because I did the dx prime integral of psi star j of x, psi of x, okay? And so this thing now that we've derived here is an integral that I can do, right? If I know what psi j is and what psi I is, right, I can do this integral over all space, and that better be the Kronecker delta, right? That is, this integral better either vanish if I is not equal to j, or it must be 1, right, if I is equal to j. And if this reminds you of what we did when we did Fourier series, that's good, right? Because all of that was about decomposing functions onto the eigenstates of the wave equation, right? And here I have a set of states that are defined by some equation. I'm not saying it's the wave equation yet, or it won't always be the same wave equation that we had in 245. But I now have a set of states, right? And the inner product of those states also obey this orthogonality, this orthonormal requirement, because it's either 0 or 1. But I want to be clear that because we've gotten to this part where we've defined what the inner product of two states are, and these are states that were generated from some operator that's not the position operator, that I can then use those, and I can write down this shorthand for how to do the inner product of psi 1 with psi 2. And this is where your book and I disagree. It took us a long time to get here, right? It took a lot of concepts to get to this point. This is not a definition, okay? This is something that is a consequence of the eigenstates, the position operator, and something that you could in principle derive, although it's something that we are going to use when we do actual calculations. And I like to call it Griffins Rule because I saw it first most elegantly written down in Griffith's textbook on quantum mechanics, and I think that it's something that we see in that book a lot and develop intuition for. But here we were able to derive it using our understanding for what it means to be a quantum system. Okay, so use Griffiths Rule, but understand use Griffiths Rule responsibly. Okay, what about expectation values? Okay, more integrals, but it's okay, right? So if I have this integral, if I'm trying to find like, what's the expected value of x, right? I can do the same thing that I always did and sandwich x in between some state, right? Again, I have, I'm going to call the bra one the x prime and the ket one the x, just so that I can put in two copies of my wave, of my state, decomposed onto the two different wave functions, right? So I have my bra copy here, and I have my ket copy here, and then I have my position operator sandwiched in between them. Of course, the wave functions are just scalars, so I can pull them out of the bras and kets. But the x operator is an operator, but when I act the x operator on x, well, I get out x times x, right? And so that's why my operator x can be pulled out of that expression, and just treated as a single number, right? Of course, I needed the fact that these are eigenstates of x in order to do that. Well, same thing happens here. This thing is x prime minus x. And I can use up that delta function by doing one of these integrals, and so I'm left with, I'll change all the x primes to x's. I'm left with dx psi star x psi of x, okay? And I'll put these on top of it as well. And so now it looks an awful lot like Griffiths Rule again, right? That I was able to use the orthogonality of the eigenstates, the position operator, to write down these expectation values in terms of the wave functions themselves and an integral. And I did promise you that the delta function would always end up in an integral, and so at least I didn't lie to you about that. Okay? So this is how I would do any expectation value, right? But I would always put that expectation value in, right? I put the operator that I'm trying to take the expectation value with respect to into this definition on the right-hand side, so that I can get out something that I can do the integral of. Okay. A lot of time spent on question 1, which was where are you? I want to spend a little bit of time on question 2, which is how much oomph do you have? And I guess that's just my colloquial way of saying, what's your momentum? Okay. Well, the momentum operator, as your book and I will say, is given by this differential. And we're going to talk a lot about why this is minus IH bar d by dx. This is probably the first time you've ever thought about the momentum operator looking like this, but I promise within the next couple of weeks, you'll wonder how you ever thought about it any differently, okay? But what this is saying is the momentum operator is a differential operator, which I've written in the x basis, okay? And now, the same way that we have this big conversation about how sometimes with the spin matrices, everybody assumes that you're working in the SZ basis, and therefore they don't even talk about it, right? They leave it off the website when they give you the spin matrices. This is the momentum operator in the x basis, in the position basis, and that's why it has this funky differential in it, this d by dx. But does this operator have eigenstates? Heck, the x operator has eigenstates. Shouldn't the momentum operator have eigenstates? Well, let's try to find them, right? So if I have my momentum operator acting on a state psi, can it obey an eigenvalue equation? That is, if I act p on psi, can I get out an answer of this is my momentum times that same state? And so to do this, well, now I'm awfully happy about having the infrastructure that I have because I can plug in my definition of a state in terms of the wave function, right? And I do it on both sides of the equation here. And when I look at this equation, the only way for this to be true is if this combination of things over here is equal to that combination of things over there, right? And so I end up with something that has a typo, but has it kind of looks like its own eigenvalue equation. That is, there's something happening to psi, which gives me my number p times psi itself. Now, this eigenvalue equation is actually pretty easy to solve because when something's proportional to its first derivative, we know what that is, right? So psi must be equal to, and I'm gonna move the things over so that d psi is it's e to the I over h bar x times p, right? And you can validate this. You can validate this yourself. If you take the derivative of this with respect to x, you're going to get I over h bar times p, and you multiply that by minus I over h bar. You just get p out in there. That solves the equation. So now I'm going to label these states with a sub p, right? So that I can say these are the wave functions that correspond to the eigenstates of the momentum operator. But much like with the position operator, these are not a discrete set of states because any value of p is going to work, right? And therefore I have something that has, for any value of the momentum, I can define a wave function that has that momentum, that can answer the question, how much oomph do you have? And it's important also to notice that p here is not necessarily positive, right? It could be positive or it could be negative. And so I have this set of states, and these are the eigenstates of the momentum operator written in the position basis, right? Where the psi sub p are going to be the wave functions that correspond to each one of those eigenstates. And a great thing to do, if you want to take a moment and say, did I understand anything Tom said for the last 33 minutes and 19 seconds? You could say, well, let me take psi of p and psi of p prime, so take two different momenta, and see what you get out, because I bet you're going to get a delta function. But it's something that I want you to, I've gone on for too long. Okay, here's your take-homes. Okay. One, we've asked two new questions today, right? The first is, where are you? Which helped us to generate the x operator as an operator that has eigenvalues and eigenvectors. The eigenvalues being like, I'm here, and the eigenvectors being every point along the real line. We also talked about the idea of a wave function, which is the function of probability amplitudes when I take my state and decompose it onto my eigenstates. We also introduced the momentum operator, which asked the question, how much oomph do you have, right? And that also had eigenstates, right? And those eigenstates in the position basis looked like e to the I over h bar p times x. And I wrote k here because I'm just that used to seeing it as a k. Sorry about that. E to the I p dot x. And then we also talked about the importance of Griffins Rule as a computational tool which will allow us to speed up things so that every time I want to take the inner product of two states with themselves, I don't always have to decompose it onto the x's and x primes and worry about the delta functions, because what we've derived for Griffins Rule in taking the dot product of two states is completely generic. Okay, that was kind of a long video and a lot to take in, but go home, now read the chapter, and you'll understand why I wanted to be so clear about these words, because we've done so much work in trying to understand the basic quantum mechanics behind all of it. Okay, see you soon.